Hello children, continuation of wave optics, that Young's double slit experiment. Through this we can easily describe how the bright and the dark fringes obtain with the help of the double slit experiments, right? So the expression for that we can see. Now this is the monochromatic light wavelength lambda, and S1 and S2, these are the slits which kept single and the double slits with the coherent source and which is separated at a distance. Now the interference fringes are obtained on the screen placed at distance capital D. We can see through this diagram. See the two slits which is there, S1, S2 are the narrow slits, and also it contains a equal distance, see, from S source. So we can derive from the same apparent source S from that, and we are getting the coherent source and which is separated at the distance D, right? And the distance, the screen distance which is capital D we have taken, right? Now the point P which is on the screen at the distance X we said from the center. Now we are going to know the nature of that. Also we know that the nature of the interference at the point B, which depends on the same phase difference and the same path difference due to that, right? Now we know that the P which is equal to S2P minus S1P. When we did S2P minus S1P, we will get the value, point value P, right? Now for that we have to take the right angled triangle. Like we have taken the small d is the distance between the two lines, is it right? The dotted line which you are seeing, the source S which is given that O, we have taken the center, right? And the two dotted lines we have it's supposed taken B and A, right, like that. From the right angled triangle we can take S2 BP and S1 AP. Like that, if suppose we have taken, means we will get what value, that S2P square minus S1P square. So this only we have taken. So we will get the distance, square of this D square plus X plus D by 2 the whole square minus capital D square plus X minus D by 2 the whole square. This came from, you have taken S2P square minus S1P square, right? That we have taken a triangle basis. So we got that S2B square plus PB square minus S1A square plus PA square. We have taken, means we will get this value. Now from D square plus that we have taken the D square plus Y plus D by 2 the whole square, right? Now for that we will get S2P minus S1P into S2P plus S1P, which is equal to 2YD. We will get 2YD value. So the del of 2D mean dy of 2D, which is equal to 2YD. So finally we will get P value which is equal to YD by D. So that YD by capital D, which we get the value. Now we can see the positions for the bright fringes and the dark fringes. This is the general value we got it. And how we will get for the bright fringes and the dark fringes we can see. For that bright fringes we will get dull which is equal to YD by capital D, that is equal to N lambda. That N lambda we got it, where N which is equal to 0, 1, 2, 3 like that we have taken, means for N if suppose which is equal to 0, Y naught which is equal to 0. Then for 1, 2 till N we have taken, means 1 suffix N which is equal to ND lambda by D, small d, got it? So this is for the bright fringes, which is nothing but constructive interferences, right? Now we are getting for the dark fringes, that is destructive interferences. Destructive interferences already we have seen that how it made, that is only we are seeing through the expression. Now dull, which is equal to yd by capital D, which is equal to 2n plus 1 lambda by 2 we have taken, right? So that till nth we have taken means we will get yn, which is equal to 2n plus 1 d lambda by 2d, right? You got it. So this is for interference occur in these points only, for the dark fringes will be formed, right? So the expression for the dark fringes width, how the fringe width will be, the bright fringe width we can see that the same thing, that is lambda n minus 1 we will get the value. So d lambda by small d. Here we have to take bright fringes. For that yn dash we can take minus 1 yn minus 1, which is nothing but we will get the expression is what, 2n plus 1 into d lambda by 2d minus 2n minus 1 into 1 plus n plus 1, sorry, 2n minus 1 plus 1 we have taken, right? D lambda by 2d. So we will get d lambda by small d. Okay. So now we can see how the distribution of intensity, the distribution curve for the intensity we can see that intensity pattern is, all the points is same. See that plotting the intensity curve, and on the bright and the dark fringes against the distance x from O, we get the curve of the intensity maximum at point O, and it becomes 0 and maximum alternate either sides of 0, it depends, right? See that the dark and the first fringe is there, like it is coming from the center bright lane, it is like center bright, from that left side if you have seen means first dark, that which one is it is going upward, that is the first bright, like that you have to take it. That means it becomes 0 and maximum alternatively either side, and also both side you have to see depending on the y, which is odd multiple dy by 2d, then integral multiple of dy by d we have to take, right? So we know that I maximum is directly proportional to a plus a the whole square, or a square. We have taken a plus a both the sides. So I maximum is equal to 4a square. So all the bright fringes have the same intensity. So if suppose I, which is equal to 0, minimum means all the dark fringes that have the 0 intensity. We can prove through the expressions also. That is nothing but the conservation of energy for that interference. This we can prove it through, right? I maximum is directly proportional to the a1 plus a2, so that we have taken a plus a the whole square. So these are the points for the maxima and minima. Maxima and minima values we are getting, and the condition for sustained interference I want. So we need the sustained interference means what is the condition for it? We have the three different the conditions, that is it must be, interference must be coherent first, and the two interferencing wave, that it must be the same plane polarizing, and the two sources must be should be very close to each other, and the pattern must be observed at the large distance, at the sufficient width for getting the fringes. Both the fringes should come in that the value of maximum and the minimum, like the way, and the sources must be a monochromatic, compulsorily monochromatic, and the fringes, otherwise what will happen, the fringes of different colors will overlap and we can't identify the overlapping colors, like, right? So the two waves must have the same amplitude, a better contrast between the bright and the dark fringes, then we will get it. So next one is the colors in thin film, that is through the ray diagram we can get how, suppose for example a soap film appears colored in white light. For that how the interference of thin film will be, we can see that, right? Now the colors are which is produced by the oil film on water and the soap bubbles, for example, we can take, right? See, this is due to because of the interference of light. You may have seen that oil film on water, a soap bubble, some colors are appeared or produced. So this is because of the interference of the light which is reflected from the top and the bottom surfaces of the thin film. See the diagram. You can take the parallel sides of the thin film. If suppose the thickness, if suppose you have taken T, and the refractive index mu. Now you are seeing the monochromatic light is incident on the upper surface first. Then this ray suffered partially, it is getting what? Reflected, and also getting refracted to that some other points, right? The parallel reflections and the refraction is going on, and the set of parallel transmitted ray also is there, right? So when these rays are focused by our eye lens, that is only the interference pattern are very beautifully visible to our eyes. The path difference between the reflected ray and the refracted ray, we have taken that as at dull, which is equal to 2 mu t cos r, where r we have take it as a angle of refraction, right? And that we have taken that r, capital R1, or we can take it here as, right, that is the reflected by the upper surface of the thin film, and it suffers an extra path difference of pi by 2 also. So net path difference, which is equal to what it will come to 2 mu t cos r, plus we have to take lambda by 2 also. So that you have to take the lambda by 2. Then for bright fringes and the dark fringes, we have to take. So we will get for the bright fringes first, we can see constructive. So that path difference, that is n plus half lambda. So we will get 2 mu t cos r, which is equal to what it will come? 2n or n plus half lambda. We will get it. Okay. And then for the dark fringes, see that OA, for the rays OA and BC, the interference, that is for the destructive, the path difference must be what? N lambda, so that we will get 2 mu t cos r, which is equal to n lambda. So when white light from the sun, which falls on thin layer of oil, which is spread over water in the rainy season, we can see that rainbow colors are formed due to the interference of light. See, when a thin film is seen with monochromatic light, suppose alternate bright and the dark fringes may be obtained, but with white light, brilliant colors are there, right? So this is because of the particular part of the thin film maybe are fixed for a particular position of our eye. So the path difference is what we said. Because of that only we will get 2 mu t cos r, right? So that is depending on that mu, that medium. That medium, it is getting varied, wavelength of the light which is get varied. So the conditions for the bright and the dark fringes are satisfied with the different positions for the different wavelengths. Because of that only we got the colored fringes, right? Okay, thank you children.